Any questions over the weekend? About anything? I like giving students a chance to ask. It's okay if not. I'm just giving you the chance. Okay. Friendly reminder then that your homework was due yesterday. You may now go back and see the answer key. Again, it'll prompt you, are you sure you want to do this? Because once you do this, I can't grant you an extension or anything because you've seen the answers, or at least as far as I know. But most of you should be prepared to go do that. Some of them have extra stuff. There's a little less this time. As we go forward, there's more and more stuff. A little more information explaining the answer, especially if that one was confusing to you, or you don't know what the answer is yet because it was numeric and you got it wrong the whole time. So, and also, I'm here too to help you with those. Yes?
The ones like the written text, like write in?
Yes. The ones where you actually have to write something out, we grade those by hand.
Okay, cool.
And basically, it's we need to go in and make sure you're not just going blah, 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 because then we just take your points away. And also that what you say makes sense.
Could you answer yes or no?
Yes or no? Well, they're not yes or no questions, are they?
It was mostly explained.
Yeah. The point of those,
It said I got it wrong.
and
I explained it correctly.
it said you got it wrong
Yeah. I don't like that no or yes.
in the essay part?
No, in the or yes.
Oh, yeah, well, if the answer is yes and you put no, then it would be wrong. And since there's only two choices there, you know what the right answer is now, so you don't get a chance to go back on that one to choose it. But then, yeah, whether you're right or wrong, and you know now, you can explain your answer. And you know what? If you said it was no, but the correct answer was yes, but you didn't know that yet because you haven't submitted it, say you answered no. Again, for those of you that are now paying attention. If the correct answer was yes and you said no, and you explained your reasoning why you thought it was no, I'm looking for logic and physics there. I won't count you wrong because obviously you explained and defended the no when that's incorrect. You follow me? I'm looking to see. The main reason I ask those, again, is that's to your benefit. You'll actually learn a lot by doing those and taking those seriously, where you have to write out, explain your answer, defend yourself. Again, when you have to verbalize what you're thinking, who's heard of the term metacognition? That's what I thought. You want to help me define it? How would you define it? Yeah, that's a little hard. It's thinking about your thinking. It's like pausing and going, what was I thinking to come up with that answer? A lot of times, especially kids, you're like, well, why'd you say that? I don't know. Well, there must have been some reason, so stop and think about what you were thinking to give that reason. I don't know. Well, you don't get anywhere there. We haven't made any progress. So when you have to stop and pause and reflect on why you're saying what you're saying and actually put it into words, seriously, you'll find your holes and you'll learn it better. You'll know, yeah, I got that. Ooh, I don't really know what to call this. So you can go look it up or make it up and then go look it up. So, point is, we grade those parts by hand, and that's what I'm looking for. Thanks for asking. Other questions? Heck, on that vein, I'm in a teacher moment. Even if it doesn't ask you to, it's not mandatory, it would be to your benefit to, you answer something. Before you move on, take 60 seconds and think about, okay, okay. That'll be good. Even better, try to explain some of this stuff after lectures to your roommates. Has anybody done that yet? Gone home and explained it to their parents, sibling, or roommate, anything? You have? Oh, bless you. Did they just look at you funny?
More or less.
But how'd you feel?
I understood it better.
Are you just saying that, or?
No, I do with chemistry.
I didn't pay him. Okay.
I do with chemistry all the time. My classmates that will ask me how does it work, and I'm like, I have no clue, but I'll explain what I think.
And just doing that helps, yeah. Hey, find buddies in your classroom. You guys are all going through the same thing, obviously. So share emails, phone numbers, the chat room, the forums, whatever works for you guys. All right, we started a chart last week. I'd like to finish it. We're talking about speed and velocity, acceleration, position, linear motion here. This one with dropping a ball. If we let go of a ball, we're investigating how its motion changes. If after a set periods of seconds, where will it be at? How much distance has it changed? What's its new position? How has its position changed? How fast will it be going? At what rate is it accelerating? When we started all this, let's fill in to where we were as a review. I started with velocity. Right when I let go, it's 0 because it's not moving. But quickly, it accelerates and gets up to a certain speed. After 1 second, how fast is it going?
10 meters per second.
Beautiful. 10 meters per second. And you knew that why? Because I told you so Friday? Yeah. Let's reason through it, though. Let's say what I was just talking about. What are you thinking? The acceleration due to gravity, we know that. It's a given. I'm rounding. 10 meters per second squared. What does that mean? What is acceleration? We defined it Friday. What is acceleration? That's right. Acceleration is a change, represented by the Greek term delta, in velocity with time. A certain amount of time. So it tells us how fast the velocity is changing. Here it changed 10 meters per second in the first second. Hence, 10 meters per second, second squared. There's our reasoning. So how fast is it going? No, I'm going to rephrase that. How much does it change its velocity during the second? 10 or 20? I heard more. Oh, now it's equal. I've heard the same amount of 10s as 20s. How much did it change its velocity during the second? Yeah. The change is 10. But it was already going 10 at the end of the first second, so now it's going how fast at the end of 2 seconds? 20. Just to emphasize that, the change there is 10. The change there is 10. What's its acceleration now? How much did it just change its velocity? 10 meters per second? In a second? 10 meters per second? It's still 10. Its acceleration is constant. Constant acceleration. The rate at which velocity is changing is not changing. I know some of this can go. So the rate at which the velocity is changing is not changing. That's the acceleration. And we can finish that one off. It's always 10. Everything when it's falling, it falls at a rate of 10 meters per second. Always. So you guys know what the rest of these are, right? You go up by 10, go up another 10, go up another 10. And you know how fast you're going. 60 seconds later, if you just let something drop, whee! Assuming it doesn't slow down from air resistance. We'll know how fast it's going. Questions on that? Terminal velocity, I'll go ahead and mention, it's when there's a balance of forces. Terminal velocity, it's you get up to a certain velocity, but it's terminal. You don't go any faster. If you're not going any faster, what's the velocity doing? Staying constant, not changing. Thus, what's your acceleration? 0. The net acceleration 0. What makes it possible for an object to slow down, to turn, not slow down, but not accelerate anymore? We'll draw on those free body diagrams. Here's an object falling. Let's name some forces acting on it. Gravity, down. That's its weight, its mass, times the g, the acceleration due to gravity. If that's all it's acting on it, what's the net force? This, and it would have a net acceleration of g. If you guys just told me the net acceleration is 0, then what does the net force have to be? 0. But wait, there's a force. What are we missing? Yeah, air resistance. So F due to air has to be equal the force due to the weight. In this case, they're balanced. But it's still moving at a constant velocity. Something can be moving and not accelerating. What do we call this? State? It's mechanical equilibrium. And since this one's in motion, you can specify it as dynamic equilibrium. As opposed to this, static equilibrium, because it's a net acceleration 0 and it's not moving. If it's going at a constant velocity, it's dynamic equilibrium, although that slowed down. But that's terminal velocity. So you'll go faster and faster and faster. Oh, now there might be enough air resistance countering its weight, and it might continue at 50 meters per second the rest of the fall. We would say 50 was the terminal velocity speed. All right, anybody remember how far it fell in the first second? Can anybody reason that one out for us? How we got that or why? That one was a little more difficult, wasn't it? Yeah.
Between the 0 and 1 second, it needs time to accelerate. So we just got to take the average of like the low, which is 0, and the high, which is 10.
Good, thank you. It accelerated for that first second, so it changed its velocity. It started at 0, ended at 10. So its final velocity after 1 second was 10. Whoops. Its initial velocity, I'm just going to say this now. I generally scientists use V naught. It's a little 0. Sometimes they use VI. I like naught more, so I tend to do it. Just, you might as well know what I'm doing. That's the initial velocity. And that was 0. So the average velocity is the final minus the initial over those two values. What's that give us? 10 minus 0 over 2, 5. So the average velocity over that first second was 5. At the beginning, you were going slower than that, and at the end, you were going faster than that. But on average, you were going 5. How far do you go? What distance do you move when you go 5 meters per second? Yeah, 5 meters. That is, again, to recognize what we're doing, distance, how far you move, is velocity times time. There's a guide to our thinking. That's what equations are in this course, in every course. The relationships. Look, if you're going 5 meters per second in 1 second, you've gone 5 meters. Look at it this way. How do we define what velocity is? It's a change in position with time. We use x generically. See, acceleration is a change in velocity with time. Yeah, well. Velocity is a change in position with time. So velocity tells us how the position changes. Whoop. All right. A little trickier. The next one. Where are we at after 2 seconds? Very good. Tell us how you got it.
You do the same thing where you have 20 your velocity minus 10 your velocity, and you divide it by 2, so you get 5 again. But you take the middle ground, the average. That's what before you get 15. You'd already moved 5 meters before, so you have to get there.
Perfect. So the final's 20, the initial's 10, so the average is 15. Please tell me, is that confusing? I know this is embarrassing for you, but because you're saying something you don't know, but we got a comfortable environment. That's why we're here. Is anybody confused why the average is 15? All right. Yeah. So final velocity, here's a way to look at average. It's the final minus the initial, the difference throughout the trip. And this, during this second of fall, from 1 to 2, we started at 10, we ended at 20. The difference, 20 minus 10, is 10. Divided by those two values, silly me. I'm wrong. I wrote that wrong. No wonder I'm confusing myself. Sorry. So see, I'm glad you asked. You were brave enough to ask. Who else was confused and saw it and was afraid to tell me? Shame, shame, shame. But good for you. I will mess up. I'm sorry. But I'll tell you when I do. So, yes, I wrote that wrong. When you do average, you add the final and the initial and divide by 2. So here, the difference is still 10. I mean, the numerator still ends up as 10 when you add versus subtract, which is why it worked out the first time and threw us all off. Okay, just me. During the second, 20 plus 10 is 30. Divide that by 2. Halfway through there, 15. Now, does everybody see that the average during the second is 15 meters per second? Whew. Okay, I'm sorry. All right, so then, yeah, if we put 15 meters per second right here, let's just go ahead and do it. Distance is 15 meters per second, because that's how fast we were going on average for how long? What's our time? How long were we going on average 15 meters per second? 1 second. It was during that second of fall. It did something else the first second, so this isn't 2. It was just happened for 1 second. So we went how far? 15 meters. During that second. Since we were already 5 down, we've now gone another 15, which puts us at 20. So I'll write that as 5 plus 15 more, 20. That make sense? Now we're solidifying it. Good. What's the average during the next second? Yeah, add them together, 50, split it in half, 25. Or you could just see halfway, it's nice and symmetric. So on average, we were going 25 meters per second for 1 second. So how far did we go? 25 more. Where do we end up? 45 meters down. I think you can see the game now. The average here? 35. So we went 35 meters in that second. Add that, what's 35 and 45? And one more. The average is halfway between, in this case, 45. That is 125. So you can see, like with our car that accelerated Friday, the spacing between positions after each second increases with each second. Here, the difference was 5. Here, the difference is 15. Here, it's 25, 35, 45. So the change in position with time is not staying constant. It's changing a different amount each second. That tells us the velocity is changing, doesn't it? And if the velocity is changing, you must have a what? If the velocity is changing, what's a change in velocity? An acceleration. So just reviewing the fact that these keep getting farther and farther and farther apart, again, tells us that the velocity is not staying constant. And if it's changing, there must be an acceleration. And how much the velocity changes tells us that acceleration. That's how we measured 10. More accurately, 9.81 meters per second squared. You guys can do it yourself. And now we can rely on it. It's kind of fun, actually. You know, when I went to the Golden Gate Bridge in San Francisco, you're not supposed to chuck things off of it, right? There's signs telling you. So I didn't. But my sister-in-law did. She spit her gum out. We timed how long it took. I honestly don't remember anymore. But you know, let's say it took 3 seconds. How far did it fall? Yeah, boom. After 3 seconds of an object accelerating it due to gravity, it'll go 45 meters. And I knew it hit the water, if 3 was right, going 30 meters per second. Again, ignoring air resistance. It's kind of fun.
Would the mass of the object also affect how fast?
Ah, good question. Good, with the mass effect. We're going to get to that next chapter even more, but I have no qualms when you guys bring up things like terminal velocity. When you're interested, that's the best time to... Do you agree these have different masses?
Yes.
So who will hit the ground first? You ready? We'll do it. Same time. Why? This one's heavier. The acceleration due to gravity is the same for both? Force times mass. Force equals mass times acceleration? So what are you telling me? The force is different?
No, just the masses are different, but the acceleration.
The masses are different, so the accelerations have to compensate. So they each fall at a different rate? What does this one fall at? 9.8, you're saying? Then what does this one fall at? Something more or less? Yeah, why does it get to be special? I don't know. In this case, it's not going to matter. Yeah, ideal. We're going to, yeah, air shouldn't matter here. Yeah, what do you want to contribute?
So since the book has a larger mass, it has more, so it has more force because it has more mass, but it also has a larger inertia. So
This does have more inertia. Things at rest want to stay at rest, don't they? If this has more mass, it has more inertia. You got that now, right? So if they're to fall at the same rate, what must the Earth do to this? Pull it harder. Which one's heavier? If you came and weighed these, which one do you think has a bigger weight? See? It is pulling with more force. Maybe we're on to something. Go ahead.
well, they're going to fall at the same rate because everything falls at the speed of gravity. But when they hit the ground, that one's going to hit harder. But it doesn't mean
The collision there could be different when the force there. Well, let's just, shut up and do the experiment, right, Adam? Okay. You ready? Did you miss it? This is a good use for a textbook, too, right? So all things do accelerate at 9.8 meters per second squared. The Earth pulls on everything so that they accelerate at the same rate. They all fall at 9.8.
So in that formula that she said, mass is different. So increase the force, then on the book integrator, the acceleration of gravity.
Yeah, let's go ahead and do that. This is Newton's second law, which we officially haven't gotten to yet, and that's okay, but I've exposed you to it. That's how you find something's weight. That's the acceleration for both objects. Let's rearrange this. The acceleration, yeah, that's what I wanted, is the ratio of force to mass. Again, if you push on something harder, it accelerates more. But if it has more inertia, thus more mass, it won't go as fast because it's in the denominator. So in our case, that's the same for both the ball and the book. The book has a lot of thank you. Has a bigger mass than the tennis ball. So what will the F's need to be? The Earth pulling on the two objects. In order to have them have the same rate of acceleration, the more massive one will have a what? A bigger force than this one to keep the same ratio. Some people, I realize letters don't make sense, but these equations are great guides to thinking. If it helps you, put in some numbers. Let's say the mass is 100 kilograms. It's not. Let's say the force then is 100 newtons. 100, 100, the ratio is 1. Over here you could have 10 and 10. See how they're smaller, but the ratio is still 1, just to help you understand it. So the takeaway here is a couple things. The book does weigh more. The Earth pulls on the book with more force than it does the tennis ball. That makes sense. So don't anybody, from here on out, because most of the layman's population don't realize this. If you ask them, they'll say, if you ask it this way, how does the force compare on the book and the ball when you drop things? They've heard that too. Oh, things fall at they hit the ground at the same time, so the force must be the same. You pull on them the same. The force is not the same. Do you see that now? The force is more on this because it has more mass. You can feel it. It's heavier. I have to exert more force to counter its weight than I do with this one. So the forces are not the same. What is the same? Acceleration, rate of change. Hence, 10 meters per second squared for everything. How about now? So if air resistance can overcome, be a big player, significant enough, compared to the weight of the object, a light coffee filter, then that can slow down the rate of acceleration. It'll change it. Without air, it goes at 10 meters per second. But if you have a countering force that's significant, what's the net force going to be? Less. So it'll accelerate at a lower rate. And it'll keep until it gets to terminal velocity that we just discussed. You know what? That was kind of fun. Since we're on it, you want to indulge me? I'll go get a cool experiment. I need about 60 seconds probably. There we are. Let's do this one. We're going to do it. We're going to get rid of air. You can go to the moon and do this, but we don't need to. I'm just going to get a vacuum pump going. And I'll pump the air out. And we'll drop them. So I have an aluminum ball and a feather. Good scientist, you do the experiment first. You need a control, right? A reference point. You know what's going to happen. Now let's get rid of the air. Close it off. Start pumping. All right. So I have two ledges, and they're held up by an electromagnet. So when I flip the switch, it'll break the current to the electromagnet, and it'll release them both at the same time. So I'm not cheating. I have to stall now while I pump air out and get air back in my lungs. And we'll see if it really works. You know a feather is really light and air resistance is significant. But if what I'm telling you is true and all things accelerate at the same rate, so you can be more knowledgeable now. Instead of saying all things fall together, you can be more, it's the acceleration that's the same, not the forces. We'll see if I'm pulling your leg. You can, if you've never done it, you can YouTube this too. They have the video of the astronaut on the moon dropping a hammer and a falcon feather on the moon because there's little to no atmosphere on the moon, so air resistance isn't a factor. All right, I've stalled long enough. Watch the bottom half. I'll count to 3 and we'll see if this works. You ready? 1, 2, 3. Woo! Physics is true. So definitely, again, which one's heavier? The ball. That means the Earth pulls on it with more force. This is my favorite part. Boom. But even though the Earth pulls on the ball with more force, it needs to. It's got more inertia to be able to accelerate it at the same rate it does the feather. Yes? Yes. Yes, and in chapter 2, it mentions Freefall. That's why. It's over here. They define freefall as the motion under the influence of gravity only. So when it says in this course, technically any time, freefall technically means you're only considering the force of gravity. That's what we did with this chart. This is how things fall in freefall. When you throw air into it, that'll start countering things. What's the net acceleration of an object at terminal velocity? 0. Very good, because it's no longer changing its velocity. What did its acceleration start at as soon as it started falling? As soon as you let go of it, it's 10 meters per second squared. See how its acceleration decreased to 0 when it hit terminal velocity? It was still falling. Its velocity was changing. It's still going faster and faster up to a point. It's just this would have decreased. It might have been 10, 9, 8, 7, 6, 5, I don't know, whatever, until the acceleration was 0, the net acceleration.
So does terminal velocity differ between different objects?
It does differ between different objects. We have a terminal velocity, but it depends on if you're in this position or this position. You fall faster like this. Terminal velocity, you'll reach a higher speed going this because there's less air drag on you than when you do this, compared to a flying squirrel who will fall even at a slower rate. So yeah, that varies. I got to do iFly this summer. It was great. Who's familiar with iFly? A few of you. There's one in Ogden. Of course, I did mine in Sacramento because it was free. I was at a teachers meeting and with the vendors in an exhibit hall, and there's somebody at a table, and they're going, "Oh yeah, we're going to have a little workshop thingy. Long story short, sign up here." And yeah. So I went, and it's indoor skydiving. You've probably seen pictures. There's a big fan. You get to get in the room, and it blows air up. And so it's like you're flying. And you can practice your skydiving skills. Granted, I'm not in there very long, but I at least got myself stable, and I got to finally experience it. Where as you move just a little bit, you change that air resistance, and yeah, you can start moving. Of course, sorry, I'm sounding all cool. Any of you ever actually skydived? Let's see, you've trumped me already, but that was cool. I liked it. Okay, let's do this. Okay, I do very few derivations in this class, and I'm not expecting you to have to repeat this. But I want to show a point here. Distance is rate times time. Velocity times time. We just did that over here. If you replace this with the average velocity, you got the final plus the initial, plus, yeah, I know, times the time. If you start at 0, like dropping something, what's the initial velocity? 0. Then you have v final over 2, because this is 0. If you start dropping something. I'm going to rewrite that. 1/2 VFT. Now, what did we say velocity was? It's a change in position with time. It's also acceleration times time, isn't it? That change. We go from 0 up to some final velocity. Acceleration is a change in velocity with time. So I'm just rearranging it. We go from 0 up to this final velocity. That's its change right here. So I'm going to take this and plug that in. 1/2 ATT, which is a very useful result. And you can understand enough how we get it. We can use this one. Distance that it moves, notice it doesn't have velocity in it. All you need to know is the rate of acceleration, the rate it changes its velocity, and you can figure out how far you fell. Go back to this chart. 1/2 AT squared. Let's do the first one. 1/2 times the acceleration. What's the acceleration? 10. Half of 10 is 5. And how long did we do that? 1 second. 1 squared is 1. So did you see how we get 5? I know. I did that all in my head. Some people don't like that. Distance equals 1/2. We went 10 meters per second for 1 second squared. We fell 5 meters. This is fun. Let's just jump right to 3 seconds. That was after 1 second. 3 seconds. 1/2. What's our acceleration? 10. How long did we fall? 3 seconds. What do we get? Half of 10 is 5. 3 squared is 9. 9 times 5. Looky there. 45 meters. It should agree. The way this changes is to the squared. The position changes with time as a quadratic. It's not a straight line. Because as the time increases, as you fall farther and farther, you change more and more distance each second. That's what this graphically represents. During the first second, you don't go up very far. You don't change your distance very far. The next second, you go up a little farther. Next second, ooh, even more. And you can see in this second, you change a lot. That's what a quadratic looks like. And it's embodied in this equation. 1/2 AT squared. That squared is important. It represents this, what we've just seen. So how I really used it on the Golden Gate Bridge was this is what I did in my head. You drop it. Go. 1001, 1002, 1003, splash. Well, took 3 seconds. I know how it accelerated. I must be 45 meters up. I'm done. You can do it in a well. I had a well when I was a kid. Drop a rock down the well. How deep is the well? Oh, it's easy. Drop something, count how long it takes. 1001, 1002, 3, 4, 5, splash. How deep's the well? 125 meters. Yeah, it wasn't that deep. Questions? All right, where am I at? Let's do this demonstration real fast and then try out the clickers and see how they're working. This one's quick. Can you see these blue marks on here? This is, as the ball rolls down it, these are, you know what? Let's turn this around. You can see it a little better. Every time it hits one of these, it's just a bump. I taped a string there so it goes clink, clink, clink. These are equally spaced. But this is accelerating down. Not as fast as straight, a little slower, but it's still accelerating down the ramp. Do you agree? So its velocity is changing. And each position, it makes a bump. Listen. Good scientists, what do you observe? It goes faster and faster. Let's listen again. One more time. As it should, because it's going faster and faster and faster with the same amount of position. So it's going to go more quickly between here and here. And so you hear it faster. Does that make sense? So you can actually apply this. That's what I did. I said, where should I put the bumps so that it sounds the same? And you get something like this. It's the same pattern as this. And like our accelerating cart Friday, do you see how they're not very far, and then a little further, then a little further, and more and more? Listen to this one. What do you observe? Yeah, even. It takes the same amount of time to go from here to here as it does from here to here and from here to here. Because it's accelerating. It's going faster down there. Galileo did a similar thing with balls and ramps and figured that out. Did an experiment, and now we can use it. All right, pull out your clickers or responseware, and we'll test this out. You'll have an idea of what it's going to be like. We got a couple minutes. We can get a couple questions in. All right. In the lower right-hand corner, if you have an actual clicker, that's the channel I'm on, 41, channel 41. So you'll need to it's the default. So if you haven't done anything, it's probably what you're on. But these need to be on that channel for me to see your answer. If you're on ResponseWare, because you're using some mobile device like your phone through your app, there's the session ID number. You'll need to enter that to join our session so that I can see yours. That's called ResponseWare if you're using that. And here's an example. What's that?
User ID.
That's the ID your ResponseWare. That's the ID you use to register ResponseWare. So I open it up by hitting play. Oh, and I can see 3 responses, 4 responses. So now you can just enter. Do you think the answer to this is A, B, C, or D? And when you enter it, you should see a check or something just validating that, yeah, it recognized you entered something. How's it working for everybody? Holler if you're getting problems here. This is a good sign then. It'll be the least amount of questions ever then. Every semester there's something that goes wrong, it seems like. What about the ID?
So it's like enter the request information at user ID. I can't even click on it.
So you registered your device in Turning Point, and you created a user ID, right?
It's not even letting me.
Couple suggestions if your ResponseWare is not working. Close it, restart it, and or turn on, off and back on. Another suggestion is, are you connected to the internet? If you're not connected to the internet, it doesn't work. And are you connected to an internet that's flaky? I don't know. The university suggests you connect to Uconnect. There's a thing right here underneath. You can't see it now, but brain lapse. Put out signal thingy. Thank you. Yeah, the modem. So it's close. It should be strong, assuming Uconnect's working. Try some of those things. Those of you that have ResponseWare, the website or the app should be free. You, of course, did have to buy a license, just like others had to buy a clicker to use it in the first place. Let's see. So we have 38 responses at the moment. If I hit stop, we can see how people answered. Success in science is linked to an emphasis on experiments or trial and error. Most of you think trial and error. Oh, you're so funny. No, there is a lot of trial and error with it through experiments. So I'm not counting these. It's not an excellent question. But yeah, the answer. So, I can close these. I can go to the next slide. Whoop. Experiments. Highlighted in blue. That's what scientists do. We try to prove things. So we do experiments. Let's try it again for some others. What's the language of science? Polling's open. You ought to be able to respond. And others can try this. Hopefully it's being happier this time. You don't know what it would be? I only know the session ID. I have no idea what your user ID is. I would suggest logging into Turning Point online and seeing your account info. Well, I hope you just have the wrong one. Otherwise, I'm kind of stumped. Wrong ID. How did yours work? Still thinking. So the way I use these often are like these type of questions, like the homework questions. Your exam questions will be similar to the homework and these questions. And so it's a chance to get some feedback before the exam so that you guys know how you're doing and I know how you're doing. We have 37 responses, 38, 39. Most of you answered A. The correct answer is A. Science uses mathematics, these equations to guide our thinking. They're just relationships to tell us how things are going to change or move. All right, we're out of time. I can now, too, see I got all your responses, whether you were registered or not. I will be able to see who didn't get points associated to them and know that something went wrong in your registration. So that I have your response, and once I get you linked, I'll know who to give credit to. I'll look for that and tell you Wednesday, those that it didn't work for.